Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Alrighty, let's make a start. So your homework was to remember where we got up to yesterday, so let's see who remembers. So we were talking about principal components. So this is this new idea of trying to take the space that you're in and rotate it into a direction that is meaningful. So what do we mean by meaningful? Well, you know, in statistics, meaningful typically means having to do with variance, right? So things that have zero variance are constant, and things that have a lot of variance are, well, by nature, random, okay? And the idea is to try and work out what's the most variable direction in the space, what's the second most variable direction in the space, right down until you get to zero variation, okay? And that's a rotation of the space. So let me show you what we've done here. So we've got this matrix X, which has a set of columns, each of which is the amount of some chemical part of cement. And the first thing we want to do is we want to take the columns of X and we want to standardise them. Okay, and the reason we want to do that is that we want it to be a fair fight between these variables X, right? We want all of the variables to have zero mean and unit variance, or variance 1. And that way we can assess their effect irrespective of scale and irrespective of centre. Okay, I want to clear out those elements, okay? So that's the first thing we do, and to create that, we first of all take out the column means. That's what this command does. And then the second thing we want to do is we want to divide through by a measure of standard deviation, which is what this part here does. Okay. Once we've done that, we apply this function PRComp, which stands for principal components, and we get this object which gives us the principal components, and it gives us the variances that go with those. So let me first of all just show you what S is. Okay, so S is this object here. It's got two elements. The first element it calls standard deviations. So these are what are called the variance components. So these are the variances that you got for the first direction, the second direction, the third direction, and the fourth direction. Okay? Now let me make this a little bit bigger. Tools, options. Seems to me a bit small. So let's see if we can... Appearance. There we go. It's a bit bigger. Is that big enough? Could even be bigger again, couldn't it? The screens in here are so small. There we go. That's nice and large. Okay. So, the first principal component, that is the first direction in this space, has standard deviation 0.431. Okay? The second one has standard deviation 0.362. The third one, 0.124. And the fourth one, 0.011. Now, what I want you to notice about that last one is that that's a lot closer to zero than the first three, right? So the standard deviations for your four principal components are big, 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 small. Now when something's got small standard deviation, small variance, it's close to constant, right? In other words, that dimension has collapsed, right? Because if something's constant, it's like saying that dimension's flat. So this tells me that my space, which I thought was four-dimensional, is really behaving like a three-dimensional space, right? Three directions have variation in them. The fourth direction doesn't. In other words, it's constant, so it's flat. All right? So right off the bat, this tells me my four-dimensional space is really a three-dimensional space hiding in four dimensions. All right? Now, the things that are given here are standard deviations, not variances. So what I really want to do is I want to square them and look at how they accumulate as I go from 1 to 2 to 3 to 4 directions. So first thing I'm going to do is I'm going to look at this set of numbers here. Now I'm going to run you through the R code because it's a little bit new. So what I'm doing is I'm taking the squares of these standard deviations, I'm turning them into variances, and then I'm going to take a running total of them as I go from 1 to 2 to 3 to 4, and I'm going to divide that by the actual total. Okay? So I'm creating percentages, running percentages. So this first number, 0.5589, so 0.56, 56%. That tells me that the first principal component, that's this first direction in this space, captures 56% of the total variation. It's over half, right? So this four-dimensional space has this variation in it. The first direction, that one-dimensional part of that space, captures 56% of the available variation. Okay? The first two together, so this says cumulative sum, so I'm taking a running total. The first two directions together, 0.952, 95% of the entire variation. Okay? So, four-dimensional space, but if I choose these two directions, which is a two-dimensional subspace, then I've captured 95% of all the variation there is in the 4D space. And that's almost all of it, right? If I've got $1,000 and I say I'm going to give you 95% of it, you're pretty happy. You got most of it, right? Well, so it is with variation. So with two dimensions, we've got 95% of the variation. If you add a third one, you get to 99.95%, right? And if you add the last one, of course, you get all of it. 4D is 4D. So, I could actually plot these things, by the way. This plot's got a name. It's called a scree plot. And what it does is it keeps track of what percentage of variation has been accumulated as you move from 1 to 2 to 3 to 4 principal components in this case. So the maximum number of principal components is equal to the dimension of the space. So here it's 4, right? Start with 0. You've got 0 directions, then you've got no variation, right? So you start at 0. With one principal component, you've got 56%. With 2, you've got 95%. With 3, 99.95%. And with 4, you get to 1. So how do you use this plot? Well, you watch and you see it rises really steeply and then it shallows out, right? So the sweet spot is where you don't get much bang for adding an extra dimension, right? So once I've got one dimension, I've got 56% of the variation. Well, 56%, it's good, but most people want more, right? Put in a second dimension, the second principal component. What do I get? I'm up to 95% of the variation, right? Well, I'm pretty happy with that. Because adding a dimension is a big deal, right? Once you're in 3 dimensions, you can visualise it, but not terribly well. Once you're in 4 dimensions, that's it. You can't visualise it at all, right? So after 2 dimensions, I've got 95% of the variation. Maybe that's it. Maybe I'm done. Maybe my 4D space is really a 2D space with a bit of noise. That's it. Okay? So this is dimension reduction. So the scree plot's a really useful plot in trying to work out how many dimensions is your sweet spot. Now, that's only the first part. What are these directions, right? I mean, I've created these new things. I've called them principal components. What the hell are they, right? You've got 4 new directions in the space. I'm telling you it's a rotation of the original set of numbers. What are these 4 directions? This is where you use the second part of S dollars rotation, okay? S dollars rotation. Let's just look at that. Now, you'll notice it's got 4 columns and they're labelled PC1, PC2, PC3, PC4. So there's your big hint. These are the coefficients of x1, x2, x3 and x4 that make up the direction. So, I'll do it longhand. PC1 equals Now I'm not going to keep all those decimal places, right? In fact, what I'm going to do is I'm going to go options digits equals 2. I only want to see things to 2 digits, right? And now, PC1, or Z1, let's call it Z1, equals 0.48 times X1 plus 0.56 times X2 minus 0.55 times X3 minus 0.39 times X4. So Z1 is, it's a line in 4-dimensional space, so it's a direction in 4-dimensional space. It is this linear combination of the x's, and that's my first principal component. That is a variable in this 4D space that has maximum variance. Okay? All right. What's PC2? PC2, called Z2. Well, you can tell me, right? It's minus 0.51 times X1 plus 0.41 times X2 minus 0.45 times X3 plus 0.60 times X4. Okay? So now I've got these two new variables, Z1 and Z2. The variation that's captured by Z1 and Z2 is 95% of the variation that exists for X1, X2, X3 and X4. So, one thing I could do is I could say to myself, why am I carrying around 4 X's when I could carry around 2 Z's and have all the same information? Right? So Z1 and Z2 could become new variables that I would use in modelling. They're my first 2 principal components. Why am I only using 2? Because I've got 95% of the variation. Probably don't need 3 and 4. Okay? What are 3 and 4? So, well, again, I know most of you will have already got it and say, no, Michael, just shut the hell up. You've told us enough. I know what you're going to do with this one. But as anyone who knows me will tell you, I never shut the hell up. Pretty much. Except when my wife tells me to, then I do. Because happy wife, happy life. Okay. There's Z3. Okay, Z3. Happy students, good too, but... Yeah. Okay, Z3. Now, Z3 captures almost none of the variation, right? So, what's another name for something that's got no variation? Constant, right? So, we think that Z3 is equal to a constant. Or close, right? Roughly. Okay, now, if I've got a combination of x's that's equal to a constant, that's a collinearity. So, the third principal component, because I think it's got 0 variation associated with it, tells me about a collinearity in the data. All right? Now, let's have a bit of a closer look at it. So, and I'm going to play a bit fast and loose here. You've got minus 0.6, say minus 0.7 x1 plus 0.3 x2 plus 0.2 x3 minus 0.6 x4. You notice that the coefficients of x1 and x4 are roughly the same. Coefficients of x2 and x3 are roughly the same. It looks like if you take minus x1 minus x4 plus about a half of x2 plus x3, you get a constant. Okay? That tells you roughly that about a half of x2 and plus x3 is roughly equal to about a half of x1 plus x4 plus a constant. Okay? That's just a rough cut. So that tells you about one of the collinearities in the space. Now, that principal component still carries about 4% of the variation, not a whole lot, so roughly constant. The last one carries almost no variation at all. You saw that it contributed almost nothing to the total variation. So it really is very close to constant. So I'm not even going to write roughly on this. It's pretty much constant. Okay? And it is 0.24 times x1 plus 0.64 times x2 plus 0.68 times x3 and plus 0.27 times x4. All right, and that's my fourth principal component. So I've got these four things. The last two are roughly constants. That tells me where the collinearities are in the data, okay? So that reveals something. The first two, I could say, okay, these are my new x's, right? Z1 and Z2, I'm just going to use them instead of the original x's, all right? Now, when people first see principal components, they get very excited. About as excited as you get in a stats class. It really is pretty exciting because, you know, people don't like having lots of x's. It's confusing, right? Like having lots of anything is confusing because you don't know what to do with it all, right? So I've gone from 4 down to 2. This is really exciting, okay? My life is made so much easier. I could actually now, I've got 3 dimensions left. I've got y, I've got Z1 and Z2. I could actually visualise that. So that's pretty cool. So people get very excited. All right. Well, best advice, calm down. Calm down. It's not that exciting. I'll tell you why. 2 reasons. Reason number 1. That combination of x's might not be all that meaningful, right? At least x1 has a meaning. It's the amount of some particular chemical in cement, right? What's Z1? Z1 is some weird-ass combination of different chemicals in cement. That might have no real meaning, okay? Now, in this particular problem, it might have a meaning because you could imagine, you know, collecting so much of this chemical and so much of that chemical and putting them together in certain combinations, and that's cool. But imagine a problem where x1 is measured in litres and it's the amount of some fluid, and x2 is measured in kilometres and it's how far someone travelled, and x3 is in centimetres, it's the length of a goat's eyelashes, and x4, God knows what it could be, right? The number of children a particular person has. All measured in different units. What do linear combinations of that mean, right? Linear combinations of these variables might be meaningful because they're probably all measured in the same units. So that's cool. Once you've got different variables with different units, principal components start to be uninterpretable, okay? And that's a problem. Because, yes, it's great to have simplicity. We've gone from 4 down to 2, and we love simplicity. But that's simplicity in terms of dimension. Now try to explain it to somebody. Oh, yeah, you take a half of the amount of blood in a goat, and you add that to about a half of the number of children that the person has, and you subtract off a half of the number of kilometres someone walked, and they're looking at you like, you didn't go to ANU, did you? You went to another university, not as good. Maybe you went to CIT, no, I don't know. You went somewhere else, you chose, you know. Do we employ you, they're going to say? Yeah, you pay me very well. No, we don't anymore. That's it, right? So explaining stuff like this is really hard. So principal components have a problem with interpretability. Okay, so that's problem 1. What's problem 2? You'll notice, you might have noticed, but if you didn't, I'm going to tell you, up until now, we've only talked about the x's. We haven't talked about the y's at all, right? And that's because y is special. Y is my response variable. It doesn't muck with the x's, okay? The idea is to relate y to the x's, okay? So now let's play a different game. Let's relate y to the z's. Now, the principal components were constructed without thinking at all about y. They only depend on x. So, who's to say that these linear combinations, even though they're the most variable in that space, have anything to do with y? Nobody. We don't know that yet. And so people sort of, when they first hit principal components, they think to themselves, wow, this is pretty exciting. I can go from a large number of x's to a small number of variables, and it's going to be all cool. If I'm really lucky, I'll go from 100 x's down to 2. Life will be great. But the problem is, you might not be able to interpret what those 2 directions mean, and then they might not even relate to y, because nothing that you've done in their construction forces them to relate to y at all. So, those are the 2 big problems with principal components. Now, when they work beautifully. In this example, they work beautifully, right? The x's are all in the same units. Even when you standardise them, it doesn't make much difference. because they're all roughly on the same scale. The x's relate to the y's, the new z's will relate to the y's as well, as it turns out. So I could play the game right down to the wire with this one. But in most problems, it just doesn't work out that way. And of course, you know, what was the great quote from Winston Churchill is that the best plans never survive first contact, right? This is a military thing. So you might have this great army and these great plans, but the first time you meet the enemy, they don't work. And then you're in trouble because you're dead, right? So, not good, right? Not good. One of my colleagues actually says, he's one of the wonderful, he's probably the best teacher at ANU actually, and his motto is that all of his innovations never survive first contact with students, right? So he's got all these great ideas about how to excite people about, he teaches physics, how to excite people about physics, but as soon as the students hear them, they go, not interested. And, you know, so that doesn't work out so well. And so principal components is a bit like that. It's a wonderful idea. It leverages one of the things that statisticians love, which is the idea that variance is so important. Variance is king or queen. And if you've got high variance, then you can use that variance to explain variation in other things. That's the whole premise of regression, by the way. The analysis of variance table is really the story of how does variation in X relate to variation in Y, right? That's the entire story of regression. And so basically all of statistics is a love story about variance, okay? You can think of it that way. And, well, I don't know how you like your love stories, but, you know, if you're a statistician, it's pretty good. You get fairly excited. Principal components is all about variation. But if variation in these two things doesn't drive variation in Y, then it doesn't get you anywhere. So how do I use principal components? Well, it's a bit like a toolbox where you have lots of different tools to do lots of different things. If I've got high dimensional data, I very often have a look at the principal components and see if they make sense. When they do, you might be onto a thing of beauty, right? When they don't, well, you've probably learned something about the effective dimension of your space, but you probably can't necessarily use that in the way that you want to, all right? Because, you know, the way you want to do it is you want to say, oh, these principal components are my new x's. I'm going to go with that. That might not work out so well, depending on the problem. But, yeah.
Sorry. How do you decide how many principal components at the first place?
So I use the scree plot. So I look at when it's steep, and then I look at when it shallows out. So basically, I just try to pick the spot where it breaks. Okay, so this is 4 variables. If I had 10 variables, it might go up for the first, second, third, fourth, then it might start to flatten out. So then I'd use 4 principal components.
So the scree plot first. And
Yeah.
decide how many.
Yeah, so you run PRComp. So the step 1, standardise your data. Step 2, run PRComp. Step 3, look at the scree plot. Use that to decide how many principal components you need. Step 4, look at the rotations and work out what they are. Step 5, go and sit in the corner and cry because they don't make any sense. Okay, that's generally what happens. That's generally what happens. Alternative step 5, cheer loudly because it all worked out beautifully and you're now viewed as a genius by everybody. But yeah, that hasn't really happened to me much. Probably won't happen to you. It might. So that's how I use principal components. So they're a nice tool and they get you so far and they get you a reasonable distance in a way that visualisation kind of can't, right? If you're in a high dimensional space, this is only 4 dimensions, which is tiny, right? But, you know, when you get out in the real world and you've got real data, you might have data that's in 100 dimensions. And, you know, there's just no hope of visualising that. You might as well just keep your eyes closed because you ain't seeing nothing, right? And so principal components gives you one shot at working out, well, what is the size of the space I'm dealing with? And going from there. And it may give you information or it may not. Now, there are some other tools. I'm going to move into fitting regular models in a second, but we are also going to talk about some non-parametric tools which look a bit like linear models but aren't, and we'll talk about how you use them as well. There's one in particular that I'll show you, which again is related to variance, and it's called additive variance stabilised models. But we'll get to them after we talk a little bit about fitting regular models. So let's talk about fitting regular models. Okay. So first thing to do is just to fit the model. So I'm going to use a linear model. I'm going to relate y to the 4x's. So we did this before, and we looked at a summary of the fit. Okay, and this is what we got. So we looked at this yesterday. So these are my coefficients, right? And these are the p-values. And as we spoke about yesterday, the p-values are, frankly, a disappointment. Because, you know, what do people normally do with p-values? You fit a big model, then you look down the list of p-values, and you pick winners and losers, right? And a winner is something that's got a very small p-value because that variable is clearly very important. And a loser is something that's got a large p-value because probably it doesn't matter. And so in this particular table here, I've got 4 losers, which is a shame, right? Because they can't all be losers, right? That doesn't make any sense. But that's how people often use p-values. Now, you know, as we talked about yesterday, and here's where we have to get really serious, right? P-values have become, I don't know, the scourge of statistics, right? Because people rely on them just far too much, and that reliance is a replacement for understanding anything, okay? And this is what happens when you have scientists who want to understand their data but don't understand any statistics, right? So here's my pitch. My pitch is, if you're a student of science or of business or of lots of other fields, but I think most people here are probably coming from science or business, you have to do statistics, right? If you don't do statistics, you're stuffed because your discipline's going to bring you data, and if you've got to outsource understanding of your own data, you've got a problem, right? But this is what happens, and it happens because of how vertical education is. And it gets more and more vertical as you get older, right? So when you're in preschool, they teach you a bit of everything. You learn about plasticine, you learn about everything. I mean, when I was in school, they taught me woodwork. I was hopeless at it, but, you know, and I still am, but I learned a little bit. I know how to use a hammer, right? They teach you stuff like that. Once you get to university, we stop trying to teach you a bit of everything. We're trying to make you experts in one thing, right? And that's problematic because that one thing doesn't live in isolation in the world. The world is a mix of everything, right? So take medical science. So doctors have to be really smart. It takes, I don't know, it takes 100 years to become a doctor. And it takes, about 10 years to become a doctor? If you want to be a good one, 10 years, say? That's a long time, right? So if you're my age, it brings you so much closer to death, it ain't funny. If you're your age, you go 10 years, that's okay. But even then you'll regret it because there's a lot of money and a lot of time, right? And you'll know a lot about being a doctor. You'll know a lot about anatomy. You'll know a lot about blood, all that sort of junk. And, so, and you might be one of the lucky ones who turns into a researcher, so you don't actually have to talk to patients. And then you get your data. And you're looking at the data and you go, okay, I've got Excel, I can probably fit a regression to this, and that's what you do. And you get a model that doesn't really mean a whole lot to you, right? And you get this big, and you've got 100 variables, say, and you've got this big table of p-values. So you run your finger down the p-values and you pick the winners and losers. Oh, that one's got a small p-value, so I'm going to keep that variable, and that one's got a big p-value, I'm going to lose that variable. And you pick winners and losers. But as you know, p-values are marginal, right? Each individual p-value tells you what that variable does if all the other ones are in there. And as soon as you start picking winners and losers, that's not the same game that you're playing. You're picking winners and losers unilaterally. You don't care what else is in there. And it just doesn't work. And so science has headed into this awful territory where medical journals are full, and not just medical journals, but finance journals, pretty much every field that has data and uses regression. They're just filled with tables of regression coefficients and p-values. And then grand declarations are made around this variable is important for explaining this variable because its p-value is small. And then people act as if that's the God-given truth, whereas in many cases it's just nonsense. So, and this is where it does get very serious, because there's an article I read, about a couple of years old now, that suggests that about 50% of studies in cancer are wrong. Just wrong. Scientifically wrong. Often because of bad data analysis, right? Often because of publication bias, these sorts of things. And that plays out really badly for people who have cancer. Not well, right? Because what happens is that doctors say, well, there's this new treatment. And all of the papers say it's really good, but the papers are based on flawed science. And then the treatment hurts the person, okay? And they're desperate anyway, right? Because they've got cancer and they don't want to die. And that's really horrible. And that's where science has brought us, okay? And it's why everybody should do statistics, right? Because everybody has to come to this road to Damascus moment that p-values aren't all it. And the problem is that even statisticians I know think p-values are all it. And most scientists I know think that p-values are all it. And it is just so misguided, right? And this example here, which is a really simple example with 13 data points and 4 x's, where all the p-values are big, shows you exactly what's wrong. Because if this was a game of picking which variables matter and which variables don't, you can't do it. Because it looks like none of them are important. And that's a problem. Okay? So, what do? Well, you have to be very careful. And you can't just rely on fitting one model, looking at the p-values and hoping that you've seen the eye of God. No, that's just not how it works, right? So we're going to have to dig deeper here, all right? So let's start to dig deeper. All right, so first thing I'm going to do is I'm just going to take each of the x's and give them names. I don't want to type CA3S and CA2S and all that sort of nonsense. I'm just going to call them x1, x2, x3, x4. Oops, I need to put semicolons in between these. Boy, didn't that get serious quickly, eh? But statistics matters. It really does. You're going, hang on, I didn't sign up for this. I wanted a relaxing Tuesday morning and nothing serious happened. I want to smile all day. Oh well. Maybe tomorrow. All right, there's my x's. All right, let's have a look at some different models. All right, so I'm going to fit a bunch of different models. First one I'm going to fit is, and I'm just going to have a look at the summary. So I'm going to go summary of LM y tilde x1. Okay, so if I only have x1 in the model, life goes back to being simple. When you've only got one x, this business where there's collinearity and you have to worry about who does what to whom doesn't apply. x1's the only one in the game, so if it affects y, you'll know, and we can tell here. So it tells me that the model is y is 81.5 plus 1.8 times x1. The multiple r squared is the number I'm going to look at, 0.534. The adjusted r squared is 0.492, so they're both about a half. So what is adjusted r squared? Well, r squared itself is just the proportion of variation explained by the model. Okay? But r squared has a problem, which is that if you just fit bigger and bigger models, then r squared just keeps going up and up and up. So there's an adjustment which imposes a penalty for large models. Okay? That's where adjusted r squared comes from. If you saw the formula, you would recognise the adjustment as being a degrees of freedom adjustment. But anyway, that's for another class. Okay? That's for, if you do a class in regression modelling, it'll all be explained in wonderful detail. But the rule in GDA is if I can't draw a picture, I can't tell you. So that's that. So, adjusted r squared is what we're going to use. So it tells you that about half of the variation is in y is explained by x1. So x1 on its own looks like a pretty good variable. Okay? All right, let's go and fit another model. Let's do y2. Okay? You can see here, there's my model. The adjusted r squared is about 64%. Now, again, I can make a comparison here because I've got like with like. I've got two one-variable models. The first one explains about 50% of the variation. The second one explains about 64%. If I've got $1,000 and I'm going to give you a percentage of it, you're going to choose the 64% one, aren't you? That's higher. right? And it seems like it's reasonably higher, right? It's not 51%, it's 64%. So pound for pound, it looks like if I had to choose a one variable model at this point, it would be the model involving x2, and x1's pretty good, but not good enough, right? And on it goes. So, x3, 0.645. Now it's getting interesting, right? x2, 64%, x3, 65%. They're about the same. This is noisy data. There's only 13 data points. So, game on. x2 and x3 look roughly like they're doing the same sort of thing. x4 on its own, 22%. Get it out of here. It's terrible. Right? 22%. So, x1 gave me 50, then I got about 65, 65, 20. Okay? So I'm already getting a picture of this by looking at different models, and I can sort of see, well, if I was forced to choose a one variable model, the best one variable model will be either the one that has x2 or the one that has x3. Okay? And then people go, well, you know, that sounds really good. Why don't we have both? x2 and x3. How can that be bad? And it turns out it's very bad, because x3 and x2 are doing the same thing. If I put both of them in, the p-values for each of them suddenly jump up really high. Together, they're just about as good as when they were apart. Look at what happened to the adjusted R squared. It went down. It went down. I'm doing worse, right? You go, how can you do worse? You've got 2. And the answer is, well, I had to add a whole new dimension, right? I'm doing worse. So x2 and x3 together, not the answer. All right, well, what about, and again, I'm going to do every 2 variable model. Lucky there's only 4 x's, right, so I can do them all. So there's x1 and x2. Oh my God, x1 and x2, I've jumped up to 97.5%. That seems even better again, right? So x1 and x2 together, 97.5. What about x1 and x3? 96.7, close, not quite. I've done x2, got to do x1, x4, 45%. That x4, what a waste of time. Okay, so we're getting a picture of our data. We've done x2 plus x3, let's do x2 plus x4. Again, x4 is dragging the chain, 82%, it's okay, but, and then x3 plus x4, 92.2%. That's x3 doing the heavy lifting and x4 getting a bit of a boost. So now I fit every 2 variable model, okay? And I'm building this picture. So if I was forced to choose one variable, I'd go with x2 or with x3. If I'm going to choose 2 variables, I'm probably going to go with x1 and x3, right, at this point. That's where I'm at. Now I'm going to fit every 3 variable model. And boy, I know that this must be a hell of a lot of fun for you guys on a Tuesday morning. But again, 97.6 if I have x2 plus x1 plus x3. But I had 97.6 when I only had 2 things. So maybe I've turned the corner. Maybe this isn't giving me much benefit anymore, right? And I'm going to see this if I add in x4, 97.6, x1 plus x3 plus x4, 97.5, x2 plus x3 plus x4, 96.4. Okay? So adding that 3rd variable doesn't really get me anywhere because I was at about 97.5 with only 2 variables, right? And then what's the last model I can fit? It's got all of them in it. And you can see 97.5 is where I land. Okay, so what you've just seen me do live is what's called all subsets regression, right? Take every combination of the x's, fit them to the y's, see what you get, compare, okay? And that's one way you can do model selection, is you just fit every model there is and see which one wins. And that's one way you can do model selection. Now, when you've got 4 x's, there are 2 to the power 4 models. 2 to the power 4 is 16. And I can do that during a lecture, right? If I've got 5 x's, there's 32 models. If I've got 6 x's, there's 64 models. If I've got 7 x's, there's 128 models. And you know where this is going. If you've got 100 x's, there are 2 to the power 100 models. And that's going to ruin your day. 1.3 times 10 to the 30. Your boss says, I need the answer by tomorrow. You go, well, I've only got 10 to the power 30 models to fit. That's a 1 followed by 30 zeros, you'd be better off walking to the moon. Seriously, right? So all subset regression is great when you don't have very many x's. That is when life is simple. But as soon as you have more than a couple of x's, you're kind of in a world of pain and you can't do it anymore, right? So it's a great idea, very simple in construction, right? But doesn't really work out so well in real life. Yeah.
I just want to ask, when we see the first one, like x1, the adjusted R squared, is it equal to the multiple R squared? Because you only
Yes.
have one of
Yes. When n is 1, the adjustment is n minus 1 divided by n minus 1, which is 1.
the result shows it's not the same.
Oh, maybe it's n minus 1 divided by n minus 2. You know, there's always a penalty for increasing the size of the model. Yeah, so it'd be n minus 1 divided by n minus 2, I think. What's 12 divided by, 11 divided by 12? 0.92. What's 0.492 divided by 0.534? 0.92. So that's where it comes from. Okay. Oh, by the way, there was one model I didn't show you. People who are counting would have said, you didn't fit 16 models, you only fit 15. Which one didn't I show you? The one with nothing in it. The one with nothing in it. Doesn't do very well. You don't use any x's. If you just pretend y is a constant all the time, you get a pretty bad model. Okay, so that one's not competitive. That's why I don't show you. All right, so all subsets regression, fine idea, but in practice, a little bit concerning. All right, so now I'm going to show you another approach, which is called stepwise regression. Now, stepwise regression, what it tries to do is it tries to fit all of the good models. Okay, now that's a pretty tough ask, right? So here's how it does it. And there are different kinds of all subsets regression. I'm going to describe the first kind, which is called forward selection. Okay? So the way forward selection works is this. So you don't need to write anything down, just listen, because R's going to do all the heavy lifting. All right? So here's how you do it. This is what R does. Say you've got a y and you've got 4 x's. Fit every one variable model. Okay? Pick the best one. All right? So in our case, that would have been x3 or x2. One of those. Forget. Okay. Now, fit every 2 variable model that involves the variable you just chose. All right? So instead of every single 2 variable model, we're only going to pick 2 variable models that have the variable you chose at step 1. Fit all of those. Choose the best 2 variable model based on that. And there you know where this is going. Then choose the best 3 variable model that has the first 2 things you chose originally, and so on, until you run out. Okay? Now, the way to think of that is that instead of having to calculate every R squared for every model, you're basically trying to skip from best to best to best as you accumulate variables. So that's called forward selection. Now, there are alternative approaches. There's an alternative approach called backwards elimination. And that starts with everything in the model and then pulls them out one at a time. And you pull out the worst one each time. Okay? And then there's an approach called forward stepwise, which does a bit of back and forth. So it says, pick the best 1 variable model, then pick the best 2 variable model that involve the first variable. Then, now you've got 2 things in the model, see if you can remove one. So you sort of do this jigsaw back and forth, and you sort of try and your model changes by 1 x in each case. So you don't end up fitting all the models, but you do fit a few more. Okay? So that's called stepwise regression. It doesn't fit every model. There is a possibility, if someone's trying to trick you, that it won't fit the best model because you might never get there, right? Because you might make a misstep early on. Maybe your best 1 variable model, you picked x3, but maybe x2 was the one you should have picked because it was the one that's the truth. We'll talk about truth another day. Okay? But it gives you some idea of what's going on in a large dimensional space without having to fit everything. Now, stepwise regression is implemented not in base R, but in a package called Leaps. So we're going to need the Leaps package. Now I don't think I've installed it, so I need to go install.packages Leaps. So it'll do that. I should have done this before the lecture, shouldn't I? Because it's going to take forever to do it. Oh, not too bad. Well, we'll see. There we go. Come on, you can do it. There, done. Okay. So, what is the command in Leaps? The command in Leaps is reg subsets. Reg subsets. Okay? Stands for regression regression subsets. So if I go help reg subsets, what? Oh, I haven't loaded Leaps yet. I'm going to go after I've installed it. I go library Leaps, very good. Then I go help. There it is. Okay. So let's have a look. So now you'll notice a lot of stuff, but the description says model selection by either exhaustive search, forward or backward stepwise, or sequential replacement. So those are the methods that we've talked about. The first one was all subsets regression, so exhaustive search, then forward, backwards, and then this back and forth, sequential replacement. Okay? Then, if you're reading the help file, you get to this and you go, oh, I feel lost now, so ignore all that. Go down to here and see what you have to give it. X. Well, X is your X values, design matrix. Y is your response variable. And then you get to specify nbest, the number of subsets of each size to record. Do you want an intercept in your model? Okay. There are some other things that people use. We're not going to worry about them. Variables you want to force to be in, variables you want to force to be out. There are good reasons why you might want to force a variable to be in. For example, it might be the most expensive variable to measure, and so you want it to be in your model, right? Or it might be a variable that's traditionally in models for this kind of thing, and so you want to be able to compare with those kinds of models. So there's all sorts of reasons you might want to force something to be in or out, but in the absence of any knowledge around why you would want to do that, we won't use that option. Okay, I love this option, really.big. So exhaustive search, like I said, you could be down for fitting 10 to the power 30 models, and R will simply refuse to do that, unless you tell it, really.big. I want to go really.big, eh? And R goes, okay. And then your computer melts. Well, that's all right, you know. One of my PhD students is doing some stuff on deep learning, and he does it all on his laptop. And his laptop actually heats up to such an extent that you can't touch it. It's so hot. And so he has to get books and put his laptop up on books and then pump a fan underneath it so that his laptop doesn't melt, right? So that's what really.big will do for you. Yeah? So be careful what you wish for is I guess, my best advice. All.best, show all the best subsets, and so on. Okay? And then there's some details here. Okay. So we're going to use this. I just want to use y, not log y. So we're going to take this. I'm just going to take the log out of here. I don't know why I've got log y there. Okay, so let's run this command. Okay, reg.subsets.out, so that's just an object I'm creating, equals reg subsets, y tilde x, I want to relate y to my 4 x's, data equals as.data.frame, cbind x and y, so that's my whole data set, all my x's, all my y's, nbest equals 10, method equals exhaustive. So I'm going to try and fit all of them. Okay, so that's the command that does it, reg subsets. Now I'm going to get a summary of the output. And now I need to make my window a bit bigger so we can see it. Okay. So none of them are forced in or out. And then these are the models that fit, right? So the first thing it did was it fit x3, then it fit x2, then it fit x1, then it fit x4, right? Then it did 1 and 2, 1 and 3, 3 and 4. So this is just a list of all the things it did. There should be 15 in this list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Missing one is the model that's got nothing in it, not competitive, so we don't fit it. Okay, so it did all of that. And then I can do this, which gives me which variables are in and out and the adjusted R squared next to it. So this is a little table that now lets me compare the models. So this is what we just, you guys watched me painstakingly fit every single model